Welcome to video number 3. I've decided that we haven't quite beat the diode to death yet, so we're going to wrap it up with a quick review and a few sample problems. All right, so we've got a typical series circuit containing a voltage source, a resistor, and what we'll assume is a silicon PN junction diode. Now, if we really wanted to analyze the circuit in excruciating detail, we would use the accurate model of the diode, which is described by Shockley's equation. Now, as we know, Shockley's equation is kind of a cumbersome exponential equation that relates diode current to anode to cathode voltage. And on the scale of currents that we're typically going to be dealing with, the diode has an effective barrier potential of about 0.7 volts. If we apply less than 0.7 volts from anode to cathode, the diode is not a very good conductor, or way over here, it's a terrible conductor in reverse bias. Okay, occasionally we can treat the diode as an ideal device. That is, it's a perfect conductor when forward biased, that is V sub AK is positive. And it's a perfect insulator when it's reverse biased. V sub AK is a negative voltage. Now, in practice, the reverse bias region of operation for a real diode is still almost a perfect insulator anyway. The current that flows under reverse bias is the leakage current of the diode, the saturation current as it's called in Shockley's equation. And remember, that's typically going to be in the nanoamp range or less for diodes that we'll be dealing with in our small signal amplifier distortion circuit, active filters, those kinds of things. All right, so a model that's a compromise between the ideal diode and actual diode is the ideal diode with a barrier potential. And that is modeled by this transfer characteristic in which we assume the diode turns on like a perfect conductor as soon as we apply 0.7 volts of forward bias. Anything less than that, and it's not turned on, it's an insulator. Turns out that's a pretty good model for most applications. Occasionally, if you have to deal with bulk resistance of the diode, that can be included by making a slope to the forward characteristic curve, but because bulk resistance is very small, typically on the order of 1 ohm or less, and compared to the circuit resistance, we can ignore it. We'll usually just go with the ideal diode with barrier potential model. All right, now let's do a couple of sample problems here just to wrap things up. All right, on the left here, we've got a circuit with a 10-volt battery that's driving a forward bias diode via a 1K ohm series resistor. All right, we know that since the diode is forward biased, that is, its anode is positive with respect to its cathode, we're going to drop about 0.7 volts across the diode. All right, we've got 10 volts applied. We're losing 0.7 across the diode. That means we must have about 9.3 volts left to drop across the resistor. Using Ohm's law, the current through the resistor is the voltage dropped across the resistor divided by its resistance. In other words, I1 is equal to the diode current, which is equal to 9.3 volts divided by 1 k ohm, which is 9.3 milliamps. So the diode current in this circuit is 9.3 milliamps. We could build that and verify it, and it would come out really, really close to that. Okay, circuit number 2. We've got 15 volts applied to, again, a series resistor with a forward bias diode. We know the diode will drop about 0.7 volts from anode to cathode. leaving the remainder of the applied voltage to be dropped across the resistor. So 15 minus 0.7 is 14.3 volts. The current, I1, which is the same as the diode current, is equal to 14.3 volts divided by 2.2 k ohms. And that is 14.3 divided by 2200, about 6.5 milliamps. So I1 is 6.5 milliamps. Very simple. The last circuit, well, it turns out it's the same as the first circuit, except the diode is in the opposite direction. That means we're reverse biasing this diode. Its cathode is more positive than the anode. In other words, V sub AK is a negative number, so it's reverse biased. That means it's acting like an open circuit, so the entire applied voltage will be dropped across the diode. If we have 10 volts here, we're going to drop 10 volts here. That leaves 0 volts to drop across the resistor. And again, I is equal to V over R. 0 volts divided by 1 k ohm is 0 milliamps. So we've got no current flow. Now, remember, in reality, we'll have a real small current flow equal to the saturation current of the diode, but that's like 1 nanoamp or so. So if we assume that I1 equals IS equals 1 nanoamp, then really this drop across the resistor is going to be, we'll call it V sub R1 is equal to I1 times R1, which is 1 nanoamp, that's supposed to be nano, times 1,000 ohms, which equals 1 microvolt. So we approximated this drop as 0 volts. In reality, it's going to be closer to a millionth of a volt, but that's small enough that I'll call that 0 milliamps. And there we go. So reverse bias diode acts like an open circuit. We've got 0 current flow. These two, we've done the analysis. We could build them. We'd find out the actual current is very, very close to the predicted value. And there you go. All right. Now, one last thing before we leave, and I kind of forgot to show you these before. If you remember, here's a silicon wafer, and we're going to create semiconductor devices out of this wafer. But the thing I forgot to show before was some masks that are used to create the patterns for the diodes or transistors or whatever we may be creating here. And here's an example of a mask. This is a chrome pattern that's deposited on a piece of glass, and this would be laid on silicon that was treated with a photoresist. It would be exposed to ultraviolet, and everywhere the UV was not blocked, we could wash that off and deposit whatever dopants that we wanted to create whatever pattern we wanted. So here's an example of a mask. Here's another mask. And I just thought that would be something interesting to show you before we close out our discussion of diodes. All right, thanks for watching. And if there's any aspect of this stuff that you think needs to be recovered or re-explained or somehow amplified on, let me know and I'll address it in the future. Otherwise, we're going to move on to some more, I hope, interesting topics. Thanks for listening, and see you next time.